Hello students, here we have few physical systems which are simple harmonic oscillators with their equations of motion and angular frequencies omega of oscillation. The first one is a mass m fixed to a wall on a frictionless plane with a spring of stiffness S, and the mass is sliding to and fro in the x direction. Such system has an equation of motion like m double x dot plus sx equals 0, having omega square equals s over m. And here we have a second physical system which consists of mass m swinging at one end of a light rod of length L. Such system has the equation of motion like mx double dot plus mg x over L equals 0, which further can be written in terms of theta like ml double theta double dot plus mg theta dot equals 0. And such system have frequency omega equals g over L under the root. And suppose there is another system having mass m at the center of a string of length 2L. What I want to tell here that is that all of these are simple harmonic oscillators which are oscillating with simple harmonic motion. I'll explain the simple harmonic motion in detail in next few slides. So here you can see when these systems are slightly disturbed from their rest position or equilibrium position, they have some equations of motion along with some angular frequencies. Now, what is simple harmonic motion? First, this is the most fundamental vibration of a single system. It is a particular type of periodic motion. In next few slides, I'll explain the difference between the periodic motion and simple harmonic motion. First, simple harmonic motion. When a body repeats its path of motion back and forth about the mean position, the body executes the simple harmonic motion. Please remember, all periodic motions need not to be of vibratory in nature. For example, the motion of the earth around the sun. Now, what is the difference between periodic motion and vibratory, oscillatory, or harmonic motion? First, periodic motion. The motion which repeats itself over and over again after equal intervals of time is called periodic motion. For example, the earth completes its one rotation on its own axis in one day and around sun in approximately 365 days. The moon completes one revolution around the earth in approximately 27 days. The third example, the motion of needles in the wall clock is also a periodic motion. Please note that these all motions keep on repeating themselves in a particular path and in a certain period of time. But the vibratory, oscillatory, or harmonic motions are those motions in which when the motion of the body is repeating itself back and forth about its mean position, then motion of such body is known as vibratory motion, oscillatory motion, or simple harmonic motion. Let's have a look this example. That is the example of periodic motion where when there is any planet moving around the sun in a specific path with over and over again, but in equal intervals of time. But this case is not the case when we have an example of mass attached to a spring, and spring is further fixed to a ceiling, wall, or something. Then you can see here that the body is doing when we apply the force on this mass, then as a result the mass is doing to and fro motion about its equilibrium position. In such case, such motion is simple harmonic motion. So please remember that each vibratory, Oscillatory or simple harmonic motion is automatically a periodic motion, but each periodic motion is not a vibratory or oscillatory motion, as we have discussed in this example. And that can, you also take the example of Earth rotates on its own axis but doesn't move back and forth about a certain point along a path. Here are few definitions which are very important to understand. For example, in the case of sample pendulum having mass m suspended with the help of a string, and the upper end of the string is attached to a rigid support. When we displace the mass m from its equilibrium position, then the distance covered by this body from its equilibrium position is called displacement. And the maximum displacement it covers is called amplitude. When the body takes time to complete one full cycle, then the time required to complete such one full cycle is called time period. And frequency is the number of complete oscillations per unit time. Please remember that time t is inversely proportional to the frequency. It means if frequency we represent with mu, that can be written as mu equals 1 over t. So you can see mu and t are reciprocal to each other. Next, to understand the restoring force, let's have a look at this example where mass m is lying on frictionless surface, and at one end it is connected to negligible mass spring, and the spring is further fixed to wall at one end. When the spring is stretched by pulling the mass m, for example on the right side, then the mass m will oscillate to and fro motion along the x-axis about its mean position. Let at some time t, the mass is at a displacement x from the mean position, but due to elasticity, the mass tends to back towards the mean position. The force that restoring mass m to its equilibrium position is called a restoring force. Here in this case, the force is proportional to the displacement x, which can be written as F equals minus kx, equation A. Please remember, K is spring constant or stiffness factor. And the negative sign means that the restoring force is always opposite in direction to the displacement, as this case happens in this example. So further equation A can be written as mx double dot equals minus kx, x double dot plus omega square x equals 0. Equation B, where omega square equals k over m, and omega is angular frequency of oscillation.